In the last video, we have seen about simple stresses and strains, but in general, the bodies are not acted with only simple stresses like only tensile force, only compressive force, only shear force. But in general, in practical, different types of stress act simultaneously, like shear and tensile will act, and shear and compressive, like that. It may act simultaneously on a body. So this analysis is called complex analysis. Complex analysis is when direct stresses and shear stresses both act simultaneously on a body. It is called as complex stress analysis. Here we do not consider bending stresses and torsional stresses. We only consider direct and shear stresses. If direct and shear stresses are acting on a body simultaneously, then it is called as complex analysis. And in this video we are going to see about that. Not only horizontal plane and vertical plane. If a body is like this, and if it is applied with a tensile force, not only this plane, there will be inclined planes also. These inclined planes are subjected to tensile force and also shear force. Due to this, the shear force also generated on this inclined plane. So if there are acting sigma x, sigma y, these are biaxial stresses, and there are shear forces tau yx and tau xy. These are acting on this body. If these are acting on this body, let us consider a plane like this. Here the plane is A, D, E, C, A. This is the plane we are going to consider now, and we will analyze the forces on this. If tensile force sigma x, sigma y are acting, and shear force tau xy is acting on this body, then how do the stresses on this body occur? So if we consider the inclined section like this, this is the inclined section, this is in 3D. The force on the left side is sigma x, and here it is sigma y, and shear forces are on this faces tau yx and tau xy. Due to this tau yx, this tau xy is generated. So these are called as complementary stresses. And the forces on this inclined plane will be, one is normal to the plane and one is tangential to the plane. That normal to the plane is called as normal stress, and this tangential to the plane is called as shear stress. This plane is called as, this inclined plane is called as oblique plane. Normal stress on oblique plane, shear stress on oblique plane. Sigma theta is normal stress on oblique plane, and tau theta is shear stress on oblique plane. This theta represents the angle made by inclined plane with the vertical. This is theta. The angle made by inclined plane with vertical is angle theta. And if we consider the diagram in 2D, we are seeing from the front side. Here sigma x, sigma y is there, and next tau yx is the shear force, shear stress, due to which tau xy is generated complementarily, and this AC is the inclined plane. Sigma theta is the normal stress on this oblique plane, and tau theta is the shear stress on this oblique plane due to all types of stresses, sigma x, tau yx and sigma y. Due to this three stresses, these are generated on this plane. So this sigma theta and tau theta, the resultant of these two stresses will be sigma r. This sigma r is resultant stress on oblique plane. Here tau xy is equal to tau yx. There will not be any difference between tau xy and tau yx, because Due to this tau ix, this tau xy is generated. So one is applied and one is generated in the body. The sign convention for shear stress should be considered like this. If it is like this, if the force is applied like it is applied like this, and the stress complementary stresses generated will be in this direction. One is this one and the other is this one. This is to be considered as positive shear stress. And if the shear stress is applied like this, if this is applied like this, the complementary are generated in the opposite direction, then it is considered as negative. So why are these positive and negative? I have posted a video on this. You can check out. The link is in the description. So remember that positive and negative sign convention for shear stress. So what are these values? Sigma theta is the normal stress on oblique plane, inclined at angle theta to the vertical, and tau theta is shear stress on oblique plane. Sigma r is resultant stress due to normal and shear stress on oblique plane. We have seen that. So what is the value of sigma theta? The derivation is not required here. Just remember the formula. So the sigma theta, which is normal stress on oblique plane, is given by tensile stress acting in x direction or axial stress acting in x direction plus axial stress acting in y direction divided by 2 plus sigma x minus sigma y divided by 2 cos 2 theta plus tau xy sin 2 theta. This is the formula for sigma theta. Sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Here, if tensile force is present, sigma is to be taken as positive. If compressive, sigma is to be taken as negative. Whether it is sigma x or sigma y. If sigma x is tensile, it is taken as positive. If sigma x is compressive, it is taken as sigma x is taken as negative. Same for the y-axis. Then what will be the tau value? Tau theta, which is shear stress on the oblique plane, is given by this formula: sigma x minus sigma y divided by 2 sin 2 theta minus tau xy cos 2 theta. This is the formula for shear stress on the oblique plane. The first one is sigma theta, which is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. And tau theta will be sigma x minus sigma y by 2 sin 2 theta minus tau xy cos 2 theta. Here cos 2 theta comes here, sin 2 theta comes here. Remember these formulas. And next will be, what will be the sigma r? So if you see the diagram, if you see this, the resultant is making an angle phi, and the resultant will be, if this is a triangle, the sigma r will be hypotenuse, and this will be sigma theta, and this will be tau theta. This is tau theta. So hypotenuse square is equal to adjust sum of squares of other two sides. So here hypotenuse square is sigma r square. So sigma r will be under root of sigma theta square plus tau theta square. This is the sigma r. And the next is angle of obliquity, angle made by resultant stress on any plane with normal stress on that plane. So this is the oblique plane, and tau theta is acting in this direction, and there is another stress, sigma theta, acting in this direction. There will be a resultant sigma r acting in this direction. Let us say angle between this sigma theta and sigma r is phi. This angle is called angle of obliquity. Angle of obliquity is angle between normal stress on any plane to the resultant stress of sigma theta and tau theta. So the angle will be, what will be the angle? If you consider this as right angle triangle, tan phi will be tan phi is equal to opposite side by adjacent side. Opposite side is this side, so which is equal to tau theta. So tau theta divided by adjacent side is this one, which is sigma theta. So angle of obliquity will be tan inverse of tau theta by sigma theta. And next is principal planes. What are principal planes is, if you consider any oblique plane, at some point the shear stress will be 0, and that plane is called principal plane. The planes on which shear stress is 0 is called principal plane. And how to find this principal plane, let us see. Normal stresses on principal plane are principal stresses. The shear stress on the plane which shear stress is 0 is called principal plane, and the normal stresses on that principal plane are called principal stresses. These principal stresses, this plane can be, if the 2D forces, 2D stresses are acting, there will be maximum principal stress and minimum principal stress. If 3D, it is a 3D stress system, which means sigma x, sigma y, sigma z are acting, then it will be then it will have maximum principal stress, intermediate principal stress, and minimum principal stress. If it is a 2D stress system, it has only maximum principal and minimum principal stress. So how many planes does 2D stress system have? 2 principal planes. It exists 2 principal planes, and if it is a 3D, it has 3 principal planes. So P1 is, let us say P1 is maximum principal stress and P2 is minimum principal stress. Let us say this angle theta is the inclination of this plane with vertical, and this plane, let us say that is principal plane, so that this sigma will be the principal stress, and this tau will be 0. Why tau will be 0? By the definition of principal plane, the shear stress should be 0 on the principal plane. So how to get the value of principal stress? So what is the condition? Tau should be 0. Tau is equal to 0 on the principal plane. What do we have the formula for sigma theta? Sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. This is what we have the formula. but this is for sigma theta, but we should write tau theta is equal to sigma x minus sigma y by 2 sine 2 theta minus tau xy cos 2 theta. So this will be 0 on the principal plane. So 0 is equal to sigma x minus sigma y by 2 sine 2 theta minus tau xy cos 2 theta, and if we send this to here, tau xy cos 2 theta is equal to sigma x minus sigma y by 2 sine 2 theta, and if we send cos theta to here, it will be tan 2 theta is equal to sending this to here, tau xy divided by sigma x minus sigma y divided by 2 is there. I am taking this to numerator. So tan 2 theta is equal to tau xy divided by sigma x minus sigma y. So this is the formula for tan 2 theta p. Sorry, this will be p. This theta p indicates that angle of principal plane with the vertical axis. So as I said, in 2D stress system there will be two principal planes. One is theta p. Let us say this is theta p1. Theta p1 is the angle of principal plane, first principal plane, and other angle will be theta p2 will be perpendicular to this, perpendicular to the first plane. One is theta p1, other is theta p2. Theta p1 and theta p1 plus 90 degrees. So what will be the value of sigma p1? Sorry, sigma 1. Sigma 1, as I said, sigma 1 is maximum principal stress. It will be sigma x plus sigma y by 2. The derivation is not required here. Plus under root sigma x minus sigma y by 2 whole square plus tau xy square. This is the formula for maximum principal stress. This stress will be on theta p1. And what is the minimum principal stress? It will be same formula will be present, but in place of plus, here the plus is there, here we put minus. That's it. Same formula, sigma x minus sigma y by 2 whole square plus tau xy square. This is at theta p1 plus 90 degrees. So one is sigma 1, which is maximum principal stress, and there is minimum principal stress. And there will be also a plane where the shear stress is maximum. So that is maximum shear stress plane. So we know the formula for maximum shear stress on a oblique plane as, so tau theta, it is represented by tau theta, shear stress on any oblique plane, which is equal to sigma x minus sigma y by 2 sine 2 theta minus tau xy cos 2 theta. This is the formula we had for tau theta. For any value to be maximum, we need to differentiate with respect to certain value, and we will get and we equate to it to 0. For maximum tau, we need tau as maximum. Differentiate this tau theta with respect to theta, we get it as, and we equate it to 0. So if we differentiate it, we get sigma x minus sigma y by 2 are constants, and sine 2 theta, differentiation of sine 2 theta is 2 cos 2 theta minus tau xy is a constant, and cos 2 theta is uh, minus 2 sin 2 theta, and minus into minus gets plus, which is equal to 0, and this will be 2 tau xy sin 2 theta is equal to minus of sigma x minus sigma y divided by 2. So 2 gets cancelled here, and the remaining is cos 2 theta. So sending this cos theta to left hand side, it will be sin 2 theta by cos 2 theta, then it will be tan 2 theta is equal to minus of sigma x minus sigma y divided by 2 tau xy. So this is the formula for shear stress plane, maximum shear stress plane, and let us say this theta is theta s. Theta s represents the maximum shear stress plane at an angle theta s to the vertical. So another plane is also present. If one maximum shear stress plane is theta s, and the other will be theta s plus 90 degrees. And also an important observation is also made, which is the maximum shear stress plane will be at an angle of principal plane plus 45 degrees. This is also an important observation that is made. Shear stress plane, one shear stress plane will be it will be equal to principal plane angle plus 45 degrees. And also another important observation that is made is, if we look at this formula, and the last one is this formula, these two are identical, but the numerator is in denominator and denominator is in numerator, and also minus symbol is present. So if we multiply these both, we get tan 2 theta p into tan 2 theta s will be equal to minus 1. So then what is the value of tau max? Tau max will be is given by plus or minus under root sigma x minus sigma y by 2 whole square plus tau xy square. This is the formula for maximum shear stress on that plane. It is also given by tau max is equal to modulus of sigma 1 minus sigma 2 divided by 2, and also given by, this is for 2D, and if it is a 3D stress system, the tau max will be, tau max is equal to maximum value of sigma 1 minus sigma 2 by 2, sigma 1 by 2, sigma 2 by 2, modulus of sigma 1 by 2, sigma 2 by 2, and sigma 1 minus sigma 2 by 2. From this, if this is the maximum, then shear stress is maximum for this. If this is the maximum value, then shear stress is equal to sigma 1 by 2. Like that, the maximum of these three values gives us the maximum shear stress in 3D stress system. The principal plane is the plane where shear stress is 0, and the normal stresses on the shear plane 0 is principal stress. But in case of when maximum shear stress is present on a plane, it does not mean that the principal stress, the normal stresses will be 0 on that plane. So normal stresses have value on that maximum shear plane also. So what will be the normal stress on maximum shear plane? So it is given by sigma theta s, or it can also be represented as sigma dash or sigma average, which is equal to sigma 1 plus sigma 2 by 2. On this maximum shear stress plane, the normal stress will be sigma 1 plus sigma 2 by 2, which is also equal to sigma x plus sigma y by 2. And there is stress formula. This is tau max. Remember these formulas: tau max and sigma theta, and what is this shear stress, maximum shear stress plane, angle with vertical. Let us see a small problem on this. The question is, find the magnitude and direction of resultant stress on BC. This is BC, principal stress on their planes. And we need to find the principal stresses and at what angle those planes are present. So how to find this? In general, we used to have sigma x and sigma y, but here there is sigma y, but the sigma x is in terms of 1000 Newton per mm. This is not the sigma x. We need to resolve this force into sigma x and the force in the direction of y. So we need to resolve this in this direction and in this direction. So this becomes sigma x, and this is acting like shear. So it will be tau xy. So in order to resolve it, so first force which we are given is directly is sigma y, which is 600 Newton per centimeter square, and sigma x will be 1000 cos 30, because it is adjacent side and the angle given is 30 degrees. So 1000 cos 30, and this will be 1000 sin 30. Tau xy will be 1000 sin 30. 1000 cos 30 is, if we calculate it, we get 866 Newton per centimeter square, and 1000 sin 30 is 500 Newton per centimeter square. If we plot the general diagram for this, so how it will be? So this is the diagram for, this is 600 Newton per centimeter square, which is sigma y, 600 Newton per centimeter square, and there is horizontal force of 866 Newton per centimeter square, horizontal stress, and there are shear stresses also. It is applied in this direction. So it is 500 Newton per centimeter square. 500 Newton per centimeter square. So this is the diagram, and we need to find the magnitude and direction of resultant stress on BC. First question is magnitude and direction of resultant on BC. What is BC? So this is BC. We need to find the resultant stress. So how to find the resultant stress on BC? So there is 500 force acting. This is the 500 Newton per centimeter square stress acting in this direction, and 600 Newton per centimeter square acting in this direction. So the sigma R will be one stress is acting in this, which is 500. Other stress is acting in this direction, which is 600. So the area of acting of stress is equal. Actually, we should not consider this 500 and 600. We should consider the forces. The force acting on BC is 500 into area, and the force acting on the normal force acting on BC is 600 into area. As this area is common for both, then so we are taking directly stresses. There will be sigma R, and sigma R will be, consider this as right angle triangle, under root of sigma y square plus tau square will be the answer for sigma R. Under root of sigma y square is 600 square plus tau square is 500 square, and the resultant stress will be 781.02 Newton per centimeter square. And direction of this one, let us say this is alpha. Alpha will be tan inverse of opposite side is this one, which is equal to sigma y, divided by adjacent side is this one, which is tau. So alpha is equal to tan inverse of sigma y is 600, tau is 500. So the angle will be 50.19 degrees. And the second problem is we need to find the principal stresses. One is sigma 1. Sigma 1 will be sigma x plus sigma y by 2. If you put plus, it is sigma 1. If you put minus, it will be sigma 2. So under root sigma x minus sigma y by 2 whole square plus tau xy square. So if we substitute the values sigma 1, sigma 2, the value of sigma x is 866 plus sigma y is 600 divided by 2 plus or minus under root sigma x is 866 minus 600 divided by 2 whole square plus the shear stress acting is 500 Newton per centimeter square, and the sigma 1 will be, if we calculate if we solve this, we get, considering plus, we will get sigma 1. Sigma 1 will be 1250.38 Newton per centimeter square, and sigma 2 will be 215.62 Newton per centimeter square. These are the principal stresses. And what will be the angle of principal plane? We know that tan 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y. So tan 2 theta p is equal to 2 into tau xy is 500 and sigma x is 866 and sigma y is 600, and we will get answer theta p1 is equal to 37.55 degrees. And what will be the another plane? Theta, let us say this is theta P2, which is perpendicular to this first plane, plus 90 degrees. So 37.55 plus 90 degrees, which is equal to 127.55 degrees. So these are the principal stresses and maximum shear stress plane, principal plane, and we have also seen first the oblique stresses. And in the next video, let us see about Moore circle. Moore circle is very important because by that a problem can be solved very easily, and also we will see about the complex strains. If this video is helpful for you, please like, share and subscribe. Thank you.